Okay, we are recording and let's get on with it. So good morning. I don't intend for this to be the last workshop session that I'll do before I retire, but we're getting close to it. I think I may have two, maybe three left, but we'll see. But this morning, this is all about CS115 and 116 conducted transients. And we'll get into the details of what all that entails. So once again, I've got some charts to at least show you the background, talk about what's actually in the mill standard and just the general principles involved, and then we'll get to play time with the equipment set up on the bench here. And you know what? Since I am retiring, I've been thinking about saying this and I'm just gonna go ahead and say it. Don't worry, there's nothing naughty or anything. I am a musician in a parallel life. And so a homework assignment for any of you who care is to see the film Pink Floyd at Pompeii. That was a film that actually changed my life. That when I first saw it, it really took my interest in music into a whole other direction. But I bring this up because right around the beginning, like after the opening song, which is part one of Echoes, one of my favorite pieces of music ever. Somebody talking? Okay, please mute if you're not specifically asking a question. Anyway, after the opening song, Echoes part one, then there's just some dialogue, some interviews with the band, and they're addressing criticisms that they've gotten for just all the equipment they use. Just, oh, you guys have all this equipment, so what? And David Gilmour makes a very interesting comment that, well, it's not just about the equipment, it's knowing how to use it that's important. And he says, I think it would be a very interesting experiment to take 4 people and just give them our equipment and say, here you go, have at it, go do something. We'll sit and watch. He said, I think it'll be a very interesting experiment. This is in his British voice. I think we'd come off better. Anyway, that's why I go through all this theory beforehand, because it's not just about going and turning knobs and on these machines over here. It's important to actually have some idea of what you're doing with it. So, end of soapbox, at least that part of it. So let's get on with it. All right, can you see the charts?
Yes, John.
Yes.
All right, I'm trying to minimize this. Well, all right, we're just gonna have to deal with that. Okay. Okay, so given the preamble, talking about CS115 and 116. So CS115 and 116 are essentially time domain equivalent test methods to CS114, which we have talked about, which is conducted susceptibility, bulk cable injection. Where CS114 injects a swept sinusoid in the frequency domain, CS115 and 116 inject transients in the time domain. And we'll plunge into the details here, in the next several slides. It uses the same injection probe as CS114 with just a couple of differences. It uses a different signal generator to generate the specified transients. And those are the boxes that are on the table here that I'll show you when we get to that part. And you monitor the injected signal on an oscilloscope instead of on a spectrum analyzer or receiver, which stands to reason if you're dealing with a time domain event, time domain transient, you want to look at it on an oscilloscope. So just a little review of the CS114 test method. This is exactly the same chart that I showed in that presentation, so we'll just go through this quickly. But is developed specifically to simulate coupled currents from incident fields. All right, so there's my cursor. And you want to have your injection probe and your monitor probe less than 1/10 of a wavelength from the EUT at the highest frequency of interest, which is 200 megahertz for CS114. We maintain that configuration for 115 and 116. And the centerpiece of all of these test methods is the injection probe. And so here's a cross-sectional view here. You provide a signal input, and there is a magnetic core there. The signal is connected to a coil of wire that goes around the magnetic core, produces a magnetic flux that goes through that core, and then that flux couples through your loop formed by the cable and your ground plane or your calibration fixture. And the time-varying magnetic flux will induce an EMF, will induce a potential in that loop formed by the cable, under test, and the ground plane. And then with all of these methods, there is a pre-calibration step, which is very important. Don't neglect this. Don't drop it. Don't let project people tell you to skip this and just get on with the test. This is part of the test, and it must be performed because this is how you know what you're injecting into a controlled fixture and controlled impedance. So you have this calibration fixture where, and I'll show them to you here when we get to the playtime part. But you have a pair of coaxial connectors on either side, and the center conductor of the coax connector feeds through the fixture, and then the shield of the coax connector connects to the base of the fixture. And here's a picture of one, much like one of the ones that I have on the table here. And so your probe clamps around the center conductor, and as you inject your signal, it produces that magnetic flux through the loop. And this is very annoying. This keeps getting in the way. Okay. And so you have a 50 ohm dummy load on one side of the cal fixture, and then you run the other side, you connect a coaxial cable up to the 50 ohm input of your measurement device. So your spectrum analyzer or for CS114, or a scope if you're using these two test methods, 115 or 116. But one way or another, you have a pair of 50 ohm loads, one on either side of the cal fixture, and your time-varying magnetic flux induces an EMF in the loop formed by the center conductor feed through and the fixture base. And you're only reading half of the injected potential. Your calibration potential, you're only tapping off of one of these 50 ohm loads, but you're inducing this EMF that is in this loop, right? So the 50 ohm resistances are essentially in series from that standpoint. So you're only looking at half of the injected potential. Okay, that I went through all that stuff with CS114. All of that is still true, irrespective of the signal source, right? Everything here is still true, no matter what source you're connecting to the signal input. Okay, so now we look at the CS115 and 116 test methods. Starting with CS115, well, you have a dedicated CS115 pulse generator. We'll get into the specifics of that. And then you're monitoring the signal on an oscilloscope. Everything else is exactly the same as CS114. Now with CS116, again, you have a dedicated CS116 damped sinusoid generator. You're looking at the signal on a scope. Everything else is the same as CS114. Okay, so all that's different is your source and how you're looking at the signal. But everything else about how you're injecting the signal and that you're monitoring the current on a current probe, it's all the same as CS114. So when you're doing these tests, it just makes sense to just do them all right in succession, right? I'm seeing that I have a typo here, so let me fix that here. But while we're here, 115 and 116. Okay. Okay. All right. So with both of these, you do a pre-calibration step, just as with 114. And again, all that's different is your signal source, and that you're looking at your signal on the 50 ohm input of an oscilloscope. For whatever reason, for CS116, they leave out that it's the 50 ohm input, but you want it on the 50 ohm input, right? It should be understood that it should be on the 50 ohm input. I don't like saying it should be understood because there are ways that things get dropped when you make that assumption, but for whatever reason, that's not on there. But it says 50 ohm input for CS115, and it's the same when you're doing CS116. All right, moving right along. Figure out how to minimize this, but here we are. I hope this isn't showing up on what people are seeing. All right, so an important thing that's marked on both these diagrams is an attenuator coming between the test fixture and the oscilloscope. So hold that thought. I'll be hitting that point hard here shortly, but clearly if there's an attenuator, that's an indication that you're dealing with some pretty hefty signals. Okay, so we'll come back to the specifics on that here presently. So you look in the mill standard, and I highly recommend you do. I mean, read through the mill standard, read through the appendix. There's a lot of good information in there. So this is right chapter and verse from the mill standard from the CS115 section. So it's called bulk cable injection, just as CS114, but it's called impulse excitation. Okay, so I'll go ahead and just read this. Is applicable to all aircraft, space, and ground system interconnecting cables, including power cables. The requirement is also applicable for surface ship and submarine systems and equipment when specified by the procuring activity. The EUT shall not exhibit any malfunction, degradation of performance, or deviation from specified indications beyond the tolerances indicated in the individual equipment or subsystem specification. I'm going to stop there and highlight that for just a moment. That is standard verbiage in the mill standard and other equivalent documents for susceptibility tests. So where it's pretty wordy and it's a bit of a mouthful, I generally in any test plans or procedures that I write or have anything to do with, I usually just copy that because that's verbiage that people who are familiar with the mill standard are familiar with. So there's no need to reinvent the wheel when you're writing a test plan. Just grab that wording. As weird and as as clunky as it might be, at least it's familiar wording. Just grab that and put it into your test plan and get on with it. So anyway, all that stuff, when subjected to a pre-calibrated signal having rise and fall times, pulse width, and amplitude as specified in figure CS115-1 at a 30 hertz rate for 1 minute. So so all the figure in question is on the next slide. So and again, picture paints 1,000 words. So the important stuff in the figure here is that it specifies a 5 amp peak by default. This is tailorable, and this is about the only parameter. Well, this and the repetition rate are the only things you really have any control over, as we'll see. But the other important things are a minimum 30 nanosecond pulse width, and more important really are the 2 nanosecond maximum rise and fall times. And you have the repetition rate of 30 hertz. And so now let's look at these signal levels. Here's where the attenuation comes into play. It's specified as a current of 5 amps peak, but you're going into a 50 ohm input of the scope to measure voltage. So 5 amps into 50 ohms is going to be a 250 volt peak. Show of hands, who wants to just go ahead and hook up a signal generator directly into an oscilloscope, just like that? Or maybe not a better show of hands, a more obvious one. How many of you want me to do that? Well, I'm not going to, but anyway, that's the point. 250 volts, not a good idea. Don't hook that directly up into your scope. So you need to attenuate the signal. So what I'm going to do here, I'm going to have 40 dB attenuation. If your scope can handle higher voltages, if it can give you 25 volts, then 20 dB will do it for you, and that's fine. But generally, at least the scope that I've got here, when you, it can give you higher voltages with the high impedance input, with the 1 mega ohm input. But when you select it for the 50 ohm input, it limits you to a plus and minus 5 volt scale. So I have to have some extra attenuation to get that into the range of something I can see, and that's not going to, overdrive the input. So just another consideration there, another test and measurement basic there. So some more verbiage from the appendix of the mill standard. Again, I can't emphasize enough, there's a lot of really good, excellent information in the appendix of the mill standard. So if you're ever in doubt about something, just open it up and read it. And even if you don't find an answer to your specific question or concern, you'll still learn something. I learn something every time I look in the appendix. I mean, just doing my homework for this presentation and grabbing this stuff, there are some additional things that I learned. So I'll just read some of the highlighted bits here. The basic concern with CS115 is to protect equipment from fast rise and fall time transients that may be present due to platform switching operations and external transient environments such as lightning and electromagnetic pulse. And the next statement I didn't highlight, but that was one of the things I had forgotten about until I looked at this again. Requirement is intended to replace chattering relay type requirements such as RS06 in Mill Standard 461C. So nobody really does RS06 anymore. In fact, I only found it in, I believe it was like Notice 4 of Mill Standard 462. So it's as the statement there, the CS115 requirement has a defined waveform and a repeatable coupling mechanism. That's one of the tremendous advantages of this type of test method, is that it is very repeatable. Some of these other test methods, like RS06, which I've never performed, so I can't really speak with authority on that, or any ESD type testing with an ESD gun, those are not very repeatable tests. There's a big variability when you apply those kind of test methods, where with CS115, it's very well controlled and repeatable. So when it says electromagnetic pulse, one of the possible applications of CS115 is to represent stimulus to a cable from an ESD type event. Just, so, and then it says here, the 2 nanosecond rise time. It's out of the way again. The 2 nanosecond rise time is consistent with rise times possible for the waveforms created by inductive devices interrupted by switching actions. The 30 nanosecond pulse width standardizes the energy in individual pulses. In addition, it separates the rising and falling portions of the pulse so that each may act independently. Okay, so there's a lot there. I'll provide my own commentary. I think that's a really nice example, nice illustration of what a lot of these test methods are about. It's not necessarily, it's certainly not intended to represent any waveform that looks exactly like the one that I showed you and what I'll show you on the scope. That's not the point. It's to provide what is, well, ideally would be a worst case type of stimulus. And if you can't get worst case, at least get something representative. So, 2 nanosecond rise time, rise times possible for waveforms and so on and so forth. So just specifying a 2 nanosecond rise time and then 30 nanosecond pulse width to give you some separation between the rise and fall times. You're never going to see a pulse that looks exactly like this one. I mean, you could, it's just not very likely, but that's not the point. This is just giving you a representative type of stimulus that you might see to see if you are susceptible to these kinds of events. And it really is the rise and fall times that are the rising and falling edges are the important parts of the stimulus. Okay. Another little bit from from the appendix of Mill Standard 461. The actual waveform on the interconnecting cable will be dependent on natural resonance conditions associated with the cable and EUT interface circuit parameters. That's a very important point, because you're going to get that nice waveform on the in the cowl fixture, which I'll show you. but when you inject in the cable, it's going to look very different. And you need, just you need to expect that it's going to, and don't be alarmed when it doesn't have that nice characteristic anymore. It's specifically those fast rise and fall times are specifically defined to exercise or excite the resonant conditions in your cable under test. Okay, so and so that we'll go through that when we get to play with these signal generators. And so there's a circuit diagram of the internals of the CS115 generator, and these are off-the-shelf boxes that you just buy. I mean, you can certainly try to build one, but there's a standard box that that's the one I'm going to show you by Solar Electronics. They make lion's share of a lot of this EMI test equipment. But there's a circuit diagram I'll show you on the next slide. So let's just go to that. So the standard box, the one I'm going to show you, the one we have in the lab here, is the Solar 9355-1. It doesn't specifically say CS115 on here, but that's what it is. And there, whatever other equivalent, like military and maybe even some commercial tests. That's why they don't necessarily say CS115, because it's not only used for that. But anyway, it's 9355. So here's the circuit diagram, and it's kind of interesting how it works. I've never actually opened up one of these things to see it, but it's actually using a piece of 50 ohm coax as a capacitor. Right? It charges up the capacitance in this length of 50 ohm coax, and then it flips this relay to discharge it into the connection that's going to the output connector. So it's charging up capacitor and then slamming the relay over to discharge it, so you get your pulse going to the output. I wouldn't have ordinarily thought to do that. That's kind of an interesting concept. But so the point is, you could try to build one of these things, but you're probably going to get a lot more reliable performance just buying it from a company who, I mean, that's what they do. They build this type of equipment for these tests. So here's some stuff from the mill standard about the test procedure. So a lot of standard stuff here. Turn on the UT, allow it to stabilize. When we get to actually testing, I'm not really going to do that. I'm just going to turn it on and show you stuff right away. But when you're doing a real test, allow, I don't know, 5 or 10 minutes, maybe just a few minutes is probably enough. But anyway, susceptibility evaluation, that's up to the providers of the equipment under test, right? They, your equipment providers have to determine how are they going to, they have to define how are they going to determine if they have a susceptibility, right? But you adjust the pulse generator for the amplitude setting, determined in the calibration step. Apply the test signal at the pulse repetition rate for the duration specified in the requirement. I believe it said it was at 30 pulses per second for, I believe it was for 1 minute. 1 minute or 5 minutes is typical. And then you monitor the UT for degradation performance during testing. That's, again, on the equipment provider. Then when susceptibility is noted, determine the threshold level in accordance with the earlier part of the mill standard. You just want to find the threshold of susceptibility, right? Then you record the peak current induced in the cable, and it's indicated on the oscilloscope. Now, this last statement here, just highlighting that in addition to common mode injection, they're saying similar to what we do with CS114, where we separate out the primary power lead and inject on it separately. So you can do that. We generally have not done that at GSFC. When we've used CS115, we've generally only done it as a common mode test. This is a judgment call that we have made. I mean, if you're dealing with some stimulus, some external stimulus, it's most likely going to be a common mode event that's stimulating an entire cable bundle and not really something that's going to be specific to a power lead, as opposed to only the power lead and not the return. Now, if you have some events that you expect on the power bus, that you think that CS115 might sufficiently represent, then sure. It's similar to what we do with oh, my mind's drawing a blank here. Well, with CS114, yes. We apply CS114 as common mode injection, but then we also do exactly this. This statement is pretty much exactly what's in CS114, where you pull out the power lead and do CS114 injection on it, but you're doing it for a different reason, and the limit is different. You're doing it to simulate uh, uh, noise or a ripple on the power bus, as opposed to potential crosstalk from neighboring cables. So with CS114, you most certainly can do the injection on the power lead. You should do the injection on the power lead, but your limit's going to be different, and you're representing a different type of event. So you can certainly do CS115 on the power leads, but just know that you're most likely representing a different event, and you might want to tailor the limit accordingly. Okay, so here's an example CS115 calibration waveform that they have in the mill standard. So if, remember the perfect waveform they had in the specification. It had a nice flat plateau on the top. This is showing some decay here between the rising edge and the falling edge. So just that amount of sag that you're going to get on what ideally is your plateau, that's going to be determined by the frequency response of your injection probe. I have one probe here. I don't think I'm going to hook it up in the interest of time, but one of the first probes that we hooked up to just test this out has a low frequency of 5 megahertz. The full frequency range for CS114 is 10 kilohertz to 200 megahertz is what we test to, but most of these probes actually are rated up to 400 megahertz. So they go down to 10 kilohertz. But with some of the older probes, like when CS114 was first introduced, you generally had two different probes, one for the low frequency range and one for the high frequency range. So this one starts at 5 megahertz. So it basically acts as a low pass filter, or I'm sorry, a high pass filter. It's filtering out the low frequencies. So it's because of the inductance, but it looks effectively like a square wave through a capacitor, through an AC coupling capacitor. That's basically what this looks like, right? So you're getting that high pass response from the inductance as opposed to a coupling capacitor, but the effect on the waveform is the same. So just be aware that if you're using a probe that doesn't have very good low frequency response, you might get something like this. But as long as your rise and fall times are coming through, all is well. Okay, shifting gears to CS116. Anybody have any questions about 115 before we plunge into this? Any indications that you're still there? An I am okay signal?
I do have one
We're
question
here.
that was sort of answered.
I got a question in the room here, so I see there's a hand up. I'll address the question in the room.
The 30 hertz repetition rate, I know it said that that's like, oh, this is just so we make sure that we don't miss anything. That seems either high or low. Is that modeled off of something like a switching relay of some kind?
I'm not really sure about that. But that's one thing we can tailor when we get to play time, that there's a knob for amplitude and a knob for repetition rate.
Yeah, I figured, but like a 30 hertz guideline seems a bit, I don't really know where that came from.
I don't really either. I know that like 60 pulses per second for CS06 was, if you wanted to sync it up to the power line frequency.
Yeah, 60 makes sense, but 30 being half of that, I mean, that's like.
Yeah.
Yeah.
I don't honestly know that. And when we have applied CS115, we generally use like 1 pulse per second.
Yeah.
So that is something that you can tailor, and these events, I don't think you're generally dealing with 30 events per second. I think you have bigger problems if you got that on your spacecraft. So I've never seen where the repetition rate is terribly important. I mean, whether you're getting this thing once per second or 30 times per second, I think it just gives you more opportunities to see it.
Yeah,
Maybe the only
makes sense.
thing.
From like a test perspective, I think that makes
Yeah.
sense.
But
But he probably came up with that number 40 years ago. It's like, that's
yeah, yes, that happens probably more times than you think, of just, yeah, 30. Anyway, question, from JP, Jeremy?
No, I was just letting you know we're live.
Okay, that's your I am okay signal? Okay.
Yeah.
All right, good. All right, well, proceeding on to CS116, let-
The upper left-hand corner, should minimize.
this, are you guys seeing the like yourselves? Are you seeing like the people screen like right in the middle of things? Or are you just seeing my charts?
I got the charts.
Okay, because there's the Teams window showing me at least a few of the people who are on. I when I'm on like full screen mode, I can minimize this. So where are you saying this is, Paul?
Upper left corner, see how it says minimize view, yeah, right.
In here?
When the minimize message pops up, click it.
Oh.
Well,
well, you don't want to click.
click the area you're at, yeah, click that.
Okay, I thought that was gonna stop the recording.
I don't think so.
It looks like it came off like, I think it's a Windows
All
side.
right, well, let's try that. Right, you're all still there, I hope. I'm just gonna come out of this for a minute, and I'm just in a slightly different configuration here, so let me make sure I'm still recording. Yep, we're recording. All right, good. It's just, there's the big red button for recording, and then the button Walt was telling me to hit to minimize that annoying little thing also had a big red button. So it looked like I was gonna stop the recording. Yeah, anyway. All this fun stuff that maybe I'll figure out by the very last presentation I give to this group. So what?
That's you have a new challenger.
Yeah, all right. So I'm just gonna read this stuff in blue verbatim. The EUT shall not exhibit any, okay, that's, remember I said the standard verbiage? We can skip over that. The EUT shall behave itself when subjected to a signal having the waveform shown, figure CS116-1, and having a maximum current as specified in figure 6, and I'll show you these figures on the next page, or next pages. The limit is applicable across the entire specified frequency range. Compliance shall be demonstrated at the following frequencies. So this is where this takes a little bit of getting used to if you're seeing this requirement for the first time. It's a little weird. But it's giving you these very specific frequencies. And when we get to the signal generator, those are the very frequencies that it provides. Surprise, surprise. So, 10 kilohertz, 100 kilohertz, 1, 10, 30, and 100 megahertz. But they specify the limit, which we'll get to as a continuous plot. So not really sure why, but I guess the next statement. If there are other frequencies known to be critical to the equipment installation, such as platform resonances, compliance shall also be demonstrated at those frequencies. So if you have some desire to test at, some other frequency, that's in between a pair of the frequencies listed there, you can do that, and then you would use the interpolated limit on the graph. So with that, let's look at the graph. So here are the two figures that are referenced from that verbiage, and we'll walk through what all this means. So it's a damped sinusoid. So there you go. That's exactly what a damped sinusoid looks like. So let's walk through what some of this stuff means here. So you have this equation here. Again, I'm the mathicist, so this makes sense to me. But if you haven't seen this, I mean, you have a sinusoid, and then you just have an exponential decay, and then this exponential decay term, whatever, minus pi ft over q. Well, they have this damping factor here, shall be determined as follows with this equation here. I really do not understand why they have specified this way. But that's what's in the document, so let's at least walk through an interpretation of this. So your Q is the damping factor, so it's just, I mean, kind of like a time constant, right? You know, if you look at a time constant, it's e to the minus t over tau. It's the same basic idea, just you know, just substituting terms a little bit here. So the Q is your damping factor, N is the cycle number. So just which peak are you looking at? You know, 1, 2, 3, 4, and so on. Then the I sub P is your peak current at the first cycle. And then I sub N is the peak current at the cycle closest to the 50% decay. Okay, so what that tells me is that this IP over IN term is just by definition approximately 2. I guess you could substitute what the exact value is, but I'm just going to use a value of 2 because that's basically what we've defined it. We're saying whatever, we're picking the peak that has the closest to the 50% decay, which here is peak number 4. But I'm getting ahead of myself. So let's get to that here now. So that's the key term here. This I sub N, peak current at cycle closest to 50% decay. So almost like I made these charts in advance or something. So the fourth peak is the one in this example, in this figure, that has our closest to 50%. It looks pretty darn close, right? So we're gonna N, that's N equals 4. So we're gonna just take our I sub P over I sub N to be right around 2. So plugging in the numbers here with 4, N equals 4, our Q is pi times 3 divided by the natural log of 2, and that's right around 13.6, which is right in the specified range. They want this Q factor to be 15 plus or minus 5. So between 10 and 20, essentially. So we're good. So it's good that whoever put that diagram together for the mill standard drew one that's compliant with their own specifications. So just looking at a couple other numbers here, if that 50% peak occurs at the third peak, well, then your Q is 9, and that's too low. N equals 5 gives you a Q of 18, so that's good. N equals 6 gives you a Q of 23, and that's out of range. So what that tells you is that your 50% peak should occur at N equals 4 or 5. I'm not really sure why they don't just say that, but there it is. I haven't really plunged into that specific definition of the Q factor. It, at first blush, seems a little more complicated to me, even to me, than it needs to be, but there it is. That's the ultimate thing there, is that your 50% peak should occur around 4 or 5. Now you're dealing with a signal generator that's just giving you the waveform, and if it's off, there's not a whole lot you can do about it other than maybe adjust some attenuation or use a different probe. That's part of what, when we get to actually showing the equipment here, I have 3 different injection probes on here, and the waveform looks the best with the one I'm going to show it to you on. So, if you're getting a really ugly looking waveform that isn't giving you compliance to this, then you may need to find a different injection probe if you have one, if you can get access to one, or play with attenuation and things like that. We'll get to that when we actually get to the demonstration. Okay, so here's the limit curve. It actually kind of has a similar shape to the CS114 curve, probably not coincidentally. But the default limit has a maximum current, a peak current level of 10 amps. Again, it's 10 amps, even though what you're measuring into a scope is voltage. So that's the very point here. A 10 amp peak into a 50 ohm scope input, that's going to give you a 500 volt peak. So there again, not something you want to do directly. So you want to put some attenuation in line with that. 40 dB or a factor of 100 will knock that down to a 5 volt peak. And that's what I'm going to show here. That'll be right at the edge of what we can observe, because with the 50 ohm input, this scope will limit you to a plus or minus 5 volt range. So there it is. If you have a scope that gets you up to plus or minus 10 volts, so much the better. And you know, if you really want better wanted to see a little bit better, you could put 60 dB in line, and it would knock that down to a 500 millivolt peak. I'm just going to go with the 40 dB because that's what I'm using across the board here, just for the sake of demonstration. So, all right. So, industry standard. Well, there are different companies make these generators, but certainly here at Goddard, we go with the solar boxes. I can't even think off the top of my head who else. I've been to support tests at other facilities where they have some other manufacturers, but these solar boxes are tried and true. I don't want to sound too much like a commercial, but you know, just solar has been around for a while, and this is what they do. They make EMI test equipment. So this solar 9354-1 is one of the standard transient. This is a CS116 transient pulse generator, a damped sinusoid generator, even though it's not really part of the title. And that's what we're going to look at here in just a moment. And so a few notes from their procedure. Once again, it says also perform tests on each individual high side power lead. Individual power returns and neutrals are not required to be tested. So there again, when we apply CS116, we generally only apply it as a common mode type of test. You know, certainly nothing is stopping you from applying it on an individual power lead, but again, know that you're probably representing a different type of transient than something that's hitting an entire cable bundle. If it's on a power lead, it's something that's happening on the power bus. So it's probably a different type of transient, and you just want to tailor the limit differently. And if you end up with the same limit, so much the better, but just put the analysis in to make sure that what you're doing is representing that type of transient and not a common mode one. One other thing I'll point out here that's somewhat unique to this test. Most of the time when you do your pre-calibration, the instructions are, I believe this is true for CS115, you do your pre-calibration, then you move the probe out of the fixture, clamp it around your cable, and you inject that pre-calibrated level. And the signal is what it is. Here with CS116, that highlighted blue statement, it says reduce the signal if necessary to produce the required current. So if you're getting, remember you're injecting into a controlled impedance fixture of 100 ohms, and when you move the probe over to an actual cable under test, the impedance is most likely going to be different, and it could be lower than that, which means you could get more current than what you've pre-calibrated. Now you're going to be limited by the 50 ohm source impedance of your signal source. So it's not going to go through the roof, but it could go to a factor of 2 or 3 times your pre-calibrated signal level. So this actually tells you reduce the signal level to get to the required current. So that's just something to note that now if your pre-calibrated level is not giving you the required current, that means the impedance of your loop is now higher, so it's limiting the current. There's no statement if you're saying increase the signal to get the desired current. Don't do that. That's how you can stress and damage things. But if you're getting higher than the pre-calibrated current, then it says you can reduce the signal to get the desired current. What that helps with, and I've done this when we've actually run this test, is if you're doing this test on multiple cables, you basically can run the pre-calibration once, to just know that you're getting the desired signal for a given signal level. But then just once you're testing the individual cables, the response is probably going to be different on each cable. I just adjust the signal level accordingly to get the desired current on each cable. Right. So especially if they're in a similar bundle, the impedances should be fairly similar. So anyway, getting pretty close to the end of this portion, and then we can start hooking up hardware. Okay, a few other, so going to the appendix of the mill standard, just some helpful information here. I'll just read the stuff in blue. The basic concept is to simulate electrical current and voltage waveforms occurring in platforms from excitation of natural resonances. So I like this statement here. In contrast to CS115 that excites natural resonances, the intent of this requirement is to control the waveform as a damped sine. Damped sine waveforms, sometimes complex combinations, are a common occurrence on platforms from both external stimuli, such as lightning and electromagnetic pulse, and from platform electrical switching phenomena. Waveforms appearing on cables can be due to the cable itself resonating or to voltage and current drives resulting from other resonances on the platform. Okay, there's a lot there, bit of a mouthful, but the real key is that CS115 is about just giving you a nice sharp rise and fall time to excite the natural resonances of of that cable or device under test, where CS116 is providing a controlled damp sinusoid from some other resonance. Okay, so that's one of the key differences there. So, all right, so here's a case study of why, of like a real world example that we encountered a couple of years ago, like why you would want to do this, you would want to apply. This is specifically CS116 we applied here. So looking at so RST Roman Space Telescope during the EMI test on the deployment, excuse me, deployment and propulsion electronics, the DPE on the ETU. Do another plug there. Doing an EMI test on an ETU, that's still a pretty good idea when you can. Anyway, it seems that's an idea that seems to be going out of fashion, but we'll keep plugging that when we can. Anyway, during that test, significant transients were measured in the time domain on cables, providing high-level pulse commands to various devices. In particular, thruster valves with inductive kickback were worst case. So I have a whole presentation on that, phenomenon and just that circuitry. That's kind of beyond the scope of what I'm going to show here, but I can make that available to anybody who's curious about it. But I mean, inductive kickback is a real thing, and as we've talked about, it's one of the things CS06 represents. So just showing here that we measured these transients in common mode, right? We're just clamping the current probe around the entire bundle, so we're not, perturbing any flight mates. So for these types of, it's more test and measurement basics here. For these types of measurements, if I don't know the frequency characteristics of what I'm dealing with up front, I like to do these measurements with two different current probes. The one on the left is the Pearson 3525. And it has a flat response from 10 hertz out to 10 megahertz. And the transfer impedance is 0.1 ohms or volts per amp into 1 megohm. Or it's 50 millivolts per amp into 50 ohms. But it's nice to go into 1 megohm because then that makes the conversion very handy. It's just a factor of 10, right? And then the Fisher F33-2, it's workhorse current probe. In fact, I have it here. You can see the camera, but we're gonna look at stuff with this here presently. It has flat response from 10 to 250 megahertz, and it's 1 volt per amp, 0 dB ohms into 50 ohms. This one's really handy because then whatever you read in volts on the scope is the current in amps. Basically, there's no conversion other than just changing the units. So the significance of the flat response is when you're doing a frequency-based test, like a frequency swept test, the flat response is not terribly important. You're taking into account the current probe's transfer impedance as a function of frequency, and and that's entered into your software and all that stuff. It does those conversions for you, and the response basically just is what it is. But when you're doing time domain measurements, having a flat frequency response is very important because then it's providing the same characteristic, same transfer function or transfer impedance to all of the frequency components contributing to the waveform. If you use a current probe for a time domain measurement that has a response that's not flat, it's going to distort the waveform. And what you see is going to be I mean, it's going to corrupt your ability to actually interpret what you're seeing. So, you know, the ideal thing to use in one of these tests would be one of those gun type current probes that's for an oscilloscope. Because then your oscilloscope will just know, oh, okay, it's this current probe, and do the conversion for you and display the current directly on the scope in amps or milliamps or whatever scale you're on. That's ideal. We didn't have one for this test, but if you have one of those, that's always your go-to device for time domain measurement. I mean, we have the standard current probes for scopes with the very small window. That obviously wouldn't work here. So you either need one of those gun type probes with like a 1-inch aperture, or you got to use one of these. And so if you're using one of these that's not specifically the gun type probe, you got to take the transfer impedance into account. And you know, if you're measuring, if you don't know the characteristics going in, then I like to use these two different probes. I mean, going down to 10 hertz, that's pretty darn close to DC. So that the Pearson is going to tell me anything, you know, in the low frequency range, and then the Fisher is going to get me from. That's actually not. That's not totally accurate. The flat response is actually from a couple hundred kilohertz, like 300 or 400 kilohertz, and up. I think I must have just thought, oh, picking up at 10 megahertz. But the Fisher probe has flat response down to a couple hundred kilohertz. So there's some overlap in the ranges where these two probes have flat response. So the significance of that is that if I get the same waveform with both of these current probes, that tells me that it's in that most of the frequency content is in that common range, which would be from a few hundred kilohertz up to about 10 megahertz. And so if the Fisher probe is giving me, you know, if I get a lot of very high frequency content from the Fisher probe that's not coming in through the Pearson probe, well, then I know I'm getting a more accurate response from the Fisher probe, and vice versa. If there's low frequency content coming through on the Pearson probe that I'm not seeing on the Fisher probe, then I know to take the reading from the Pearson probe. So done this type of thing a lot, right? So we take measurements. Sometimes I just put both current probes on the cable at the same time. And in fact, I probably did, because the plot I'm going to show you has them both. So so here the waveforms, and just note that both scales are set to 100 milliamps per division. So the yellow trace is 100 millivolts per division. That's the Fisher probe. So that's the one ohm transfer impedance. So that's 100 millivolts equals 100 milliamps. And then the Pearson probe is 0.1 volts per amp, or 10 amps per volt. Okay, so at 10 millivolts per division, that's the same as 100 milliamps per division. And it's going into the 1 megohm input, right? That transfer impedance, you know, it goes down by a factor of 2 if I go into the 50 ohm input. So all these things to keep in mind when you're doing all this stuff. So, but anyway, I know I'm looking at these two on an equivalent current scale. The waveforms look pretty, not identical, but pretty darn similar. So I can basically believe either one of them. And the Fisher one's a little more sensitive. So I think I probably just continued to use this one. Anyway, it's not completely a damped sinusoid, but it's pretty darn close. I mean, it's something at least a damped sinusoid could represent. It's got about a 1 microsecond ringing period and about 170 milliamps peak current. So this was what we were measuring from the turnoff transients from those inductive loads, from those thruster valves. And then when we looked at the implications of this, so as the DPE, the deployment propulsion electronics, the signals on those cables where we were seeing those transients. Well, unfortunately, this was why you do unit level tests. More commercials, more public service announcements. Why you do unit level tests? This was this is a CAD drawing well in advance of when we actually integrated the spacecraft. This stuff is all integrated now, right? We're in environmental testing at space, at mostly observatory level. But this was, I don't remember, a good year or so before we were starting integration. But we had this CAD layout showing, you know, okay, we're going to be bundling these cables with the cables from the telescope control electronics. Right in the same bundle. There's no separation. Everything's right in the same bundle. So, anyone for crosstalk? I don't play tennis, so I'm not going to ask anyone for tennis. Let's just go straight to crosstalk. Now, crosstalk is going to be a very significant risk here. So what are the implications, right? So, I went to the project and especially to the owners of the TCE. That was most of this platform is built in-house, but TCE and the whole telescope was provided by a nameless external contractor. But I went to them, and I had actually been the electrical systems lead for the telescope for a bit before I, became the EMI lead for the program for a while. So I knew all these people, and I went to them and showed them the results and said, "Hey, is this something you guys might be concerned about? Or I think you should be concerned about. We should at least look at it." And long and short of it was, okay, the telescope, as you can imagine, the telescope control electronics, it's controlling a lot of like motors and other mechanisms and stuff like that. The risk of that type of transient corrupting a motor drive is slim to none. That's not really where the concern lies. The concern is on low-level analog telemetry lines, position sensors, temperature sensors, and stuff like that. My thermal brethren would probably not be happy to hear this, but when are thermal people ever happy with electrical people? I don't know. But if you get an erroneous single reading on a temperature sensor, to me that doesn't spell disaster, right? But if you get an erroneous reading on a position sensor that's part of a control loop, and then the control circuitry in the TCE, interprets that as a real movement and then starts providing correction to move that mechanism when it doesn't have to, that's much worse. That really is not something you don't want to go in that direction, right? So, I'm trying not to say the name of the contractor, I almost did, but they appreciated the input, and it turned out that the most sensitive lines they had, I don't know if they were position sensors or temp sensors, but whatever it was, the analog sensors, they did a lot of averaging. Like they did 256 averages as a group, and they did multiple groups of those. Long and short of it was that the worst case was that this type of event would perturb one, maybe two samples out of easily hundreds, if not a couple thousands. And the very worst case was that it might produce about a half an LSB of error in one of those averaged readings. And just by analysis, they said, okay, this is not a big concern. But I strongly advocated, and they fully agreed. Now let's go ahead and apply CS116. It was not applied as a requirement. This wasn't a going in requirement. So, but we added it to the TCE test plan as engineering data only. So it's just another public service announcement here. When you have a concern like this, well after you've defined your requirements, go to the project and make your case. Okay, we have this concern that's not adequately addressed by our existing requirements, but here's this test that we can run for engineering data to give ourselves some assurance that this is not going to be a problem on the integrated platform. And when I walked through all of the rationale, there really was no pushback. Maybe initially, but once we made the case and we said that this is a test that we can run in maybe an hour, maybe 1 or 2 hours, and it was worth that investment of time to retire this risk. We were able to do it, right? Now, the default peak current specified by CS116 is 10 amps. And the capacity of the generator includes headroom. You can get, I think, maybe about 15 amps out of this thing. But remember that what we measured was about 100. The worst case peak we measured was a little under 200 milliamps, 170 milliamps. So applying 10 amps, okay, that's overkill. So we tailored that down to 1 amp, a 1 amp peak current. And the repetition, the ringing period was about a microsecond. And so we said, okay, we don't need to apply every single one of these frequencies. We can just apply it at 1 megahertz and 10 megahertz to kind of bracket the range of where that ringing we observed. That was sufficient to represent this event that was of concern. So we did it at 1 amp peak, 1 megahertz, 10 megahertz, and no susceptibilities were observed during the test, and we retired the risk. And we haven't seen any indications of this being a problem on the integrated spacecraft. So anyway, that is what I have for the preamble. And so anybody have any questions before we play with some hardware? Okay. Yeah, are you seeing the view in the lab full screen?
Yes, we are.
Okay, excellent. Okay, I shouldn't need to go back to the charts unless there are any specific questions, but so first time I'm doing this here, so I'm having to recalibrate as we talk about calibration. So, all right, so turning you all toward our equipment here. So here's the CS116 generator, Solar 9354. We'll get to that. We're going to start with CS115. I mean, since I talked about CS115 first, I couldn't possibly show you CS116 first. That would go out of order and that would be wrong, wouldn't it? Can't do it. Just, James fully agrees. That would not be acceptable. So we'll start with CS115. Thanks to Walt for finding the extension cord. So I have to move my computer with the camera. So here is the CS115 generator, model 9355-1 pulse generator. Again, different manufacturers make versions of this. I've seen some, I cannot remember the nameless contractor that I successfully didn't mention. They can't remember the manufacturer of their system, but it's a combined system that does CS115, 116, it might even do CS101. But it's a microprocessor based and it was very finicky. Yeah. What as you'll see from these boxes, they're well, you know, going to my musical background, right? You know, I recently bought, well, recently a couple of years ago, I bought a new tube amplifier, which is just wonderful. Like guitar players, we love our tube amps, right, Nick? Do you own a tube amp?
I do, but I mostly play digital, so.
Yeah, okay. Well, so Nick is the digital advocate here, but it had been a while since I owned a tube amp, and vacuum tubes still have a place, certainly in audio. They just really sound sweet, especially when they're overdriven. Tube distortion is just a thing of beauty. But anyway, that's kind of the thing with these boxes. They're just good solid workhorse boxes. You turn them on, you get your waveform, and then they just work. So we'll get to that here. I'll just show you the basic setup. You have the output connector here, and we'll turn it on in a second. You can adjust the amplitude and the repetition rate. That's it. The rise and fall times and the duration are just set by the unit, and if those are not in spec, then you need to have the unit serviced or replaced. But when it's built to spec, it just works until small war story. I actually managed to, well, we like to tell the story that I broke this unit a year or two ago. I let it run for an overnight test and it was no longer working in the morning. I don't believe that we had it set for any unusually high signal level. So I was blamed just because I was the last one to use it. But other than that, they're workhorse machines. So there's a cable going into our, I'm going to disconnect this from the stand. Oh, sorry, Walt. So this comes back around. This is the input connector to the probe. So this is this test probe. that we'll be using for these demonstrations. This is the solar probe that I mentioned. Oh, I said 5 megahertz. This thing actually starts at 2 megahertz, so it's even worse than what I said. Right? That this probe is not going to give you as good response for CS115, right? And then here's another probe, Fisher F120-8. So I'm going to just do everything with this Tessic probe, but whatever probe you have in your lab, I mean, that's what you get, that's what you use. So our signal comes in to the input connector and it generates the magnetic flux that wraps around, couples through the loop formed by your center conductor and the base of the fixture. Now we have our 50 ohm dummy load here on one side, and then we have 40 dB worth of attenuation here, and these are some of the higher power attenuators. I can't actually read the power rating. I don't know if it's 10 watts or something. 50 watts. Okay. For these impulses, it's less critical that they necessarily have high power, because power is generally about, continuous signal, right? For these impulses, you can probably get by. I don't know why I'm telling you this, but you can probably get by with lower power, but it never hurts to have good higher power attenuators when you're dealing with signals like this, because they are pretty beefy signals. So as I mentioned, we're looking for 5 amps into our 50 ohm input of the scope. So we're looking for 250 volts. Okay, so the pair it's pair of 20 dB attenuator, right? So 40 dB total, factor of 100. That's going to knock the signal down to 2.5 volts. So that's what we're going to be looking for on the scope. Okay, this is stuff that you just need to get, you need to just get used to doing these kind of conversions, because you have to deal with this all the time. Like, what are you seeing on the scope, and then how does that relate to the thing that's really happening, right? You got to bear in mind 2.5 volts on the scope means 250 volts here. So you're dealing with some pretty hefty signals here. So, all right, with all that, let's turn this thing on. And
Great. Motion segment.
like I said, I hope I didn't make everyone see so. All right, so let's turn it on. So I'm starting with that specified repetition rate. I don't know if you can hear the clicking online. People in the lab, I'm sure can, but that's your repetition rate. So it's just over 30 pulses per second. That's pretty annoying, unless you guys like it. But but when I was just checking this out, I was doing it down at about 1 pulse per second. But actually, the scope is triggering a little more solidly here, so we'll leave it alone for the moment. And so all you get to control is the amplitude, the fine adjustment of pulse per second, and then the 3 buttons here are the band for the repetition rate. All right, you go down to band 2. And it knocks it, I believe each one is probably a factor of 10. So that sounds like about 3 pulses per second. And then down here, it's even slower. But we'll keep it up here for the moment to get a good trigger. And here, all right, so here. Once someone goes. Yeah. Action. Okay, so there's our signal on the scope. I'm going to set it for single trigger. You see there's a little bit of variability, which, I mean, kind of be expected. I wouldn't get too upset about that. But we go to normal triggering and then single trigger. All right, now we can turn that off so we don't have to hear the relay clicking. So we're at 1 volt per division. So that's 2.5. There we are, 2.5 divisions. There's our 2.5 volts. That's what we wanted. And our we're at 20 nanoseconds per division. So we'll go ahead and do more continuous trigger because I want to adjust a few things. So let's adjust the time base. Okay, well, now we're at 10 nanoseconds per division. So a little more than 3 divisions. So that's good. That we're hitting the 30. It says 30 nanosecond minimum pulse width. All right, so it's 32, 33 nanoseconds. We're good. Again, there's nothing we can do about it. It's whatever it's what the generator is producing. And then the other important bit was the rise and fall time. So let's expand around there, and I'm gonna move my trigger level lower so I get a little bit lower on the waveform so I can see more of it. I'll also move the trigger position over if I have to, but that's okay. Nope.
Still works.
Okay, I'm gonna go back to single trigger just so we have a.
Still works.
There. All right, then we turn that off. So now we have just. We just have a single trace that we can just look at here. So now we're at 1 nanosecond per division. And so our rise time, I mean, if you define it strictly as 10 to 90%, that's right around a nanosecond. It's certainly less than 2 nanoseconds, right? And it's indisputable that it's under 2 nanoseconds. So it's in spec. So all of these captures are part of what you would want to get screen captures of all this for your test report. You know, the pulse width is giving you, greater than 30 nanoseconds. You zoom in on the rise time. For completeness, we'll look at the fall time too. Oh yeah. So there we go. And then we'll do our single. All right, there we go. And so the fall time is a tiny bit longer, but it's still under 2 nanoseconds. So it's 1 nanosecond per division. So we're triggering there. So it's comfortably under 2 nanoseconds, about 1.2, 1.3 nanoseconds. So there you go. That's pretty much it. Except for one additional point. Let's go back to, did anybody notice anything else about the waveform? Let me show you the whole thing here. Does that look ugly or does that look pretty? I mean, it is what it is. I mean, if you applied the waveform this way, it wouldn't necessarily be bad. But what that tells me is that it's not necessarily impedance match, right? The output impedance of this generator is supposed to be 50 ohms, but the calibration fixture is not actually presenting 50 ohms. Remember, it's presenting 100. So it's not actually a full impedance match. So this is not something in the mill standard, but something you can do, which I'm going to show you right now. Let's turn this off. The standard technique when you've got an impedance mismatch is to put a pad in line. So got 6 dB pad here. Yeah. We labeled our pads nicely here. So whenever you put a pad in, it's a juggling act, right? The higher value of your pad, the better match to 50 ohms you get, no matter what the physical termination impedance is. I did a demo that included this at the EMC symposium last year. I don't know if I've done it. I don't think I've done it here for this group. But I mean, you can work through the math and you can hook it up and convince yourself that like with a 20 dB pad, an open circuit looks like 51 ohms, something like that. Or 30 dB pad, an open circuit looks very close to 50 ohms, like 50.1. And a short circuit looks like 49.9. Ballpark. Right, and then with a 20 dB pad, 50 an open circuit may look like 55 ohms or something. 10 dB, it's like 62 ohms or something like that. But And, you know, so from that standpoint, oh, well, let's just put a 40 dB pad in there, and then we know we've got 50 ohms, no matter what we put at the output. Well, you're attenuating the signal by 40 dB. So you have to determine how much of a pad is just enough to minimize the impedance mismatch, but where you can still get the signal that you're trying to get. So 6 dB, I mean, doing this experimentation here, we've done this before. 6 dB seems to be about right here. So it's knocking the amplitude down by a factor of 2. But well, let's go back over here and see for ourselves. All right, so actually that's good. We still have that waveform from before, so you can see it's almost a full division of junk here. That's about a third of the amplitude of the intended signal we're getting from this. And you know, it was different. You know, we were getting variability from each cycle, right? So let's go back to full auto triggering. This thing back on. Now, okay, our trigger's too high, right? It's knocking our amplitude down by a factor of 2, as we expect. So now we got to crank the amplitude up. Fortunately, we have enough headroom to do that. So we'll turn the amplitude up. Actually, I misspoke. That's full scale now. So you can't get the full 5 amps with the 6 dB. In fact, I think I tried with 3 dB and we weren't quite able to get to the 5 amps. But if you apply a tailored limit, say with a 1 amp limit, that's what we've done in some cases. If 1 amp is sufficient to address your concerns, well, you can certainly get that. So let's go back down to an amp. So I believe, yeah, 1 amp. 1 amp in 50 ohms, 50 volts, 40 dB of attenuation is 500 millivolts. Okay, so let's go to, what's that?
It was at 666.
Oh, these guys were entertained that the amplitude shown on the display here was 666. I didn't even do that on purpose. I wish I did. The amplitude of the beast. All right, so now we're at 200 millivolts per division. So if we were going to apply a tailored limit of 1 amp, again, just can't work through the math too many times where they're concerned. 1 amp into 50 ohms, 50 volts through 40 dB of attenuation is half a volt, 500 millivolts. So we're able to get that signal with the 6 dB of attenuation in line with the drive signal. And if we go to our single trigger, the additional junk here seems to be it's cleaned up a bit. It's not perfect, but it's cleaned up some. So again, this is the sort of thing you just have to use your judgment. If you need the full 5 amp signal, like a lot of times that if you're testing for some external entity that is just saying, nope, this is the requirement and you must test to the full 5 amp level. Well, it is what it is, and you're not gonna, at least with this signal generator, you're not gonna be able to put any attenuation on. Even the 3 dB attenuator didn't allow us to get the 5 amps. It is what it is, and the signal and the signal you're applying is ratty. But you know, you're applying, you know, a pretty aggressive waveform, and you know, you want it to just be responding to the you know the fast rise and fall time, but there's that additional stuff there that you can't do a whole lot about. But that's and that response is going to likely be a bit different for each probe. So you would just have to experiment with the different probes you have at your disposal. That black probe, the one that starts at 2 megahertz, that gives you a waveform that's a bit closer to what's in the mill standard. It has pretty significant decay here, and then the falling edge, you know, goes like it basically gives you what a square wave into AC coupling would look like. So anyway, all of this is, all of what I'm doing here is it's not intended to be like, this is the answer, that this is exactly what you do under all circumstances. It's giving you the engineering basis to make some of these decisions, understand what it is you're trying to do and how to best get the test equipment to give you the results that you want. But if I'm applying a 1 amp signal, I call that pretty good. I mean, I wouldn't spend a whole lot of time trying to muck with this. I think even with the one amp, we might have been, I think we may have been able to put 10 dB of attenuation in line. But again, I'm not going to take any time to do that now. But I think I'm going to turn this back on and then we'll switch over to CS116. With the attenuation, you're able to get the amplitude of the drive signal up higher. This actually be more evident. I'm going to show you this with CS116. These drive amplifiers don't really like being down at the lower end of their scale, and so let's see how far down we are here. It says 329. I think that means millivolts, but okay, so there's 0. And full scale is about 1200. So we're at about quarter scale, right? But when you want to be up like half scale or higher, because then you're in the more stable part of the operation of your box, and you have a little more granularity, right? If you're down at like 5% scale, on your potentiometer, any little adjustment you make is a pretty significant change. We saw that with CS116. It was hard to really dial in a desired amplitude if there's any little change on the knob on the potentiometer was a pretty significant change in the signal level. So when you put some attenuation on, if you're looking for a smaller signal than what the unit's capable of, you put some attenuation on it, then you can drive the amplifier to closer to the full scale where it likes to be, and then use the attenuation to your advantage to get the signal down into the lower range that you want. So that's what I have for the CS115. Any questions on this before we move to CS116? Okay, so I'm gonna move over here. Oops, sorry. Okay, so the only difference is the signal generator. So here's this 9354 we talked about. Here are the different outputs. So 10 kilohertz, 100 kilohertz, 1, 10, 30, and 100 megahertz. Everything is powers of 10. For whatever reason, they threw in 30 megahertz as well. So go figure. So if you're using this specific box, there's a different connector for each for each frequency, and then you also have to turn the knob so that it's pointing to the one you want. That's a very easy mistake to make. It's also very easy to figure out that's what's wrong. I'm on the 10 megahertz output. Why am I not getting anything? Well, because I'm pointed at 1 megahertz. So so let's hook this thing up, and then we'll show what it looks like. I'm only going to show the 10 megahertz waveform in the interest of time, but again, if you have access to this equipment in your EMI lab, I fully encourage you to hook it up and play with it a little bit and get accustomed to it. And it's always a good idea to just get familiar with the test equipment with non-flight hardware before you ever hook it up to flight hardware. That's kind of a crazy heretical statement, but okay. So we have our signal coming out of the 10 megahertz output. The knob is switched to that. We'll adjust the amplitude. I believe I did adjust this earlier, but we'll see what happens. Here's the power switch. So this box actually has an enable, or once you turn the power on, then well, it says automatic or manual, right? It's on the manual setting right now, and then you can hit this button for a single pulse. Oh, I'm sorry. Thank you. Well, there's this automatic manual switch. So when it's on manual, basically the output is disabled and until you hit the single pulse button. So I like to turn it on with it in that position, so it acts as an enable switch. That I can turn the unit on, but I'm not getting any signal out of it until I tell it to, either by flipping it over to automatic where it gets a repetitive pulse or it hits single pulse. The 115 generator doesn't really do that. So, I don't think the CS116 generator does either. So, all right, we're gonna go ahead and turn this thing on. And go over to automatic. I don't know if you can hear the clicking, but here it's pretty much 1 pulse per second. I believe that's the specification, and that's all you get. There's no adjustability on that. So, fix my scope. There it is. And if that's the CS115 generator signal still up there. Yep, we're getting a signal. So remember, if we want 10 amps is the default for this signal. 10 amps into 50 ohms is 500 volts. To the 40 dB of attenuation is 5 volts. Okay, and so now we're on 1 volt per division. And let's trigger was pretty low, so it's getting a lot of spurious stuff there. All right, so that's giving us a good trigger. Do a single trigger and then let it stop. Okay. So the peaks are coming right up to about 5 volts. So that's the limit that this scope will provide. Turn that off. So if I wanted a little better resolution around that peak, I might put another 20 dB of attenuation so that it's 500 millivolts. But here we are. We'll leave it like this. So the lower peak is coming right up against that limit or the edge of the display of -5 volts. The upper peak is maybe just shy of that. We could tweak that, but you get the idea. That it's giving you that 5 volts, but then prior to the 40 dB of attenuation, that's your 500 volts. And then into 50 ohms, that's your 10 amps. Okay. And then remember that you want the 50% peak to be around the 4th or 5th peak for full compliance. And so the 3rd peak is around 60%. That's 3 volts out of 5. And then the 4th peak is about 40%. So we don't have a peak that's like right at 50%, but effectively it would be between the 3rd and the 4th peak. So that's okay. Remember that the 3rd peak was just barely out of the specified range, like 9 or something. 9 where the range is 10 to 20 for that Q factor. So again, there's not a whole lot you can do about it. I mean, you can't adjust this on the signal generator, but with some of the other with one of the other probes, I think we were not quite getting we were getting an uglier waveform. So, but this is pretty good for if 10 megahertz is the signal that you're wanting to apply. I mean, that's about as good of damped sinusoid as you're going to get. That's clearly what it is. It's a damped sinusoid, and you're saying, okay, it decays more or less to 0 up to about here. So now 10 amps is a pretty significant level. As I said, we on RST, when we observed this type of behavior, but at a lower amplitude of a few hundred milliamps, we said, okay, if we're going to apply this, we don't want to apply 10 amps. That's kind of overkill. So let's apply 1 amp. It gives us a little bit of overhead margin above the 170 milliamps we observed. So let me start by just doing that. Let's back to automatic triggering. Okay, so we're triggering again. So, so if we want 1 amp into 50 watts, but basically it's gonna go down by a factor of 10, right? We're at 10 amps. So we're at 5 volts peak. We want to get down to 500 millivolts. Okay, so I'm first gonna just do that with the way it's set up. Then we're gonna change our vertical scale. Yep, there we go. Change vertical scale. So now it's at 500 millivolts per division, so we still need to come down a bit. All right, so now we're at 200 millivolts per division, so we want to be basically 2.5 divisions. All right. That's pretty good. I guess we'll go with that. Do a single trigger. Okay. Now we're not getting nearly as many cycles. And if push came to shove, that would be okay. We probably applied this. You're still getting a damp sinusoid transient. Your 50% point now looks more like peak 3. So it's not fully compliant. Again, I know not. It's called, they touted as a requirement. I don't know how, I mean, again, the generator gives you what it gives you. But what I think is very significant here, I haven't put any attenuation on the drive line, but look at where the knob is. You can actually, there is a mark on the knob here. So, I don't know if you can make out the scale here, but I believe that's 12%. So we're a little bit less than 12%. We're at maybe 10% full scale. So as I said, a lot of these drive amplifiers don't like operating down that low. You just don't have a lot. They're less stable. They're a little more finicky, technical term. So here again, for a little bit of a different reason, where we put the pad in line, that 60 dB pad in for the for CS115 for impedance matching. Doesn't seem to be much of an indication of an impedance matching problem here, but just to be able to drive the amplifier closer to full scale, where it's happier, where it's more stable, we'll go ahead and put some attenuation in line with the drive signal. Is this okay? 20 dB. Now this is a brick. This is probably overkill for what we're doing here. It's 200 watts. You can see that. But it's here, and so I'm going to use it. But you could probably get by with a lower wattage. But 20 dB is what we want. I mean, we want to go from 10 amps down to 1 amp. That's factor of 10, so 20 dB. So then we can basically use the same setting we had before, where we were getting that nice waveform, but then we're just going to knock it down by a factor of 10. So let's go ahead and put this thing in place. Yep. I've done other demonstrations with using BNC cables. I mean, we don't have the RF performance of N cables, but they're much easier and quicker to make and demake. But here we are. Oh, something else to pay attention to. A lot of these attenuators are bidirectional. Doesn't matter which way you come out. This one, this one's marked. A lot of the ones we have here are marked input and output. I think, I don't know if that's so much the circuit topology as much as just for these higher power ones, I mean, it's basically just like a resistive network. You want your higher power resistor to be on the input side. or resistors. So whatever resistors are dissipating a higher power, that's what's on the input side. So when it says input and output, make sure you pay attention and hook it up right. All right, then we've got. Now we've got our 20 dB attenuator in line. And that's just signal generator going through input of the 20 dB attenuator and coming out into the injection probe. Everything else is the same. So now we'll turn this power still on. Now we just enable the output. And now go see what our signal is like. Broke good, but you know. All right, that's the stored waveform from before. So let's. Okay, so it's still set very low. We're probably not. Okay, we're barely triggering the scope. Okay, but we want to get our 1 amp. Okay, so let me go back to the 1 amp that we went through is the 500 millivolts is what we want. So it's vertical scale is now 200 millivolts per division. So we want to get up to two and a half divisions. Cranking this up. Almost there. That's all right. It's a little high, but I'm going to take it down just a little bit. Sometimes the first negative peak actually has a higher amplitude than the first positive peak. So you can just use your judgment there, you know, level on either one of those. I tend to level on on the leading peak, right? And if the first negative peak's a little higher, then don't worry about that too much. Okay, let's do a single trigger. Okay. All right, that looks pretty much like the waveform we had before, just knocked down by a factor of 10. Kind of like what you want with a 20 dB attenuator in there. And now our halfway magnitude is right around between the third and fourth peaks. It's pretty much exactly like what we had before. So, if you want to tailor it to a lower limit, again, if you're tailoring it by something like a factor of 10, then putting a 20 dB pad in line is in this particular case is much more effective than just turning the drive amplifier down to almost zero. So that's just generally a good practice is put an attenuator in line and drive your amplifier to the higher end of its scale. So that's all the pre-calibration. And now our sample unit under test has been in the other room. We're not going to move all this stuff into the other room. I'm just going to, for injecting into example signal, I'm just going to use a wire. So let's get our probe out of here. So these fixtures generally have a removable lid. So thank you.
Shut it down first.
Yes, thank you, Greg. It's the output's disabled, but yeah, turning the power on is a good idea too. Yeah, don't do this sort of thing with a hot signal. That's one thing where the clicking is nice. The clicking is very annoying, but when you don't hear the click, then the output is not enabled or not energized. This particular probe has this screw on here. Others just have clasps that are much easier and quicker to remove, but there we are. But this probe has a little better performance for what we're doing here, so much the better. Okay, so there we can get this out of the way. We don't really need, actually, I think we do want the attenuators. So. Thank you. All right, so for when you're injecting into the cable under test, you want to keep the drive configuration. So if you used the attenuator for the calibration, you leave it in. You can adjust the attenuation on the monitor side as needed. But the drive circuit up to the probe should be the same. I mean, so we're just gonna, like, the lowest impedance you can inject into is, I mean, if you're injecting into a shielded cable with the shield terminated to chassis at both ends, it's basically gonna be a short circuit, at least at low frequencies. Then your loop inductance is gonna kick in at higher frequencies and things like that. So generally, for just demonstrating purposes, I just take a piece of wire and short the ends together to give. There you go.
Apparently I'm touching my lock button.
Well, Sloan is talking.
Gemini wants to talk to us. For TBI.
Okay. Well, so I just use a piece of wire that's, that's just connected to itself. Just gives me a loop. So at low frequencies, it's a short circuit. And then you're going to get, inductive reactance as a function of frequency. So, and you get a handy dandy insulator. One of the manuals that we have sitting here. And now remember when I said that when you're looking at a time domain waveform, so we're monitoring current, right? So we're going to put a current probe on our cable or wire under test. This is the workhorse F33-2 probe. See the part number right there. And it has a 1 ohm transfer impedance from about 300 kilohertz up to 250 megahertz. So for our 10 megahertz signal, even down to our 1 megahertz signal, this will be well suited to that. I'm only going to show you the 10 megahertz out of in the interest of time. But yeah, just when you're monitoring current, you just got to make sure you're using a probe suited to the frequency range you're dealing with. Oh, Greg has a more official insulator. What we use is our 5 centimeter spacers in the lab. So we're more official now. Thank you, Greg.
That was expertise.
Okay. So give credit where credit is due. All right, so let's think about the levels here. We're looking for 1 amp, right? So for what we just pre-calibrated to, right? So the probe's transfer impedance is 1 ohm. So 1 amp of current that it's measuring is going to give us 1 volt. So for that, we don't really need any attenuation. Okay. So if we wanted 10 amps, then 20 dB of attenuation ought to be enough, because then 10 amps, 10 volt. If you had a high voltage setting on the scope, you might not even need it then, but we do for this scope. So I'm just going to take the cable, go into the scope. I'm going to remove the attenuation. And then we should be able to see our waveform on the scope. Again, you're depending on your probe to have flat transfer impedance across the frequency range of interest. This is kind of a kludgy setup, but you'll get the idea. So we'll turn the signal generator on. Everything should be the same as what we just left it for, right? So we're still set for 10 megahertz. The drive amplitude to give us 1 amp into our cal fixture. Now turn the generator back on. That's our calibrated signal. And let's go back to proper triggering. There we go. Getting a good beefy signal. And okay, this actually is a good illustration of one of the points in the mill standard. Now here, we'll go with a single trigger. Let's just see what we're dealing with before we muck with anything. There, our leading edge is negative. Which isn't a big deal, it's just the way I've got the current probe oriented. So we could just go with what we got, but then, if you wanted to call me OCD, guilty as charged, that does bother my aesthetic sensibility, so I'm gonna flip the current probe around. So, all right, now our leading edge is going positive. Everyone else feel better?
Yes.
I think, you can't flip the polarity with a switch on this generator. On CS115, you can. There is that, I should have pointed that out. All right. Over here. There is actually a switch right underneath the power switch. On the CS115 generator, you could flip the polarity right here. No, you can't do that on the CS115. But because you're getting, the transient is giving you positive and negative going pulses, it doesn't really matter. But anyway, this is one of the points that was made in the mill standard. If we go to single trig and stop. We pre-calibrated to 1 amp. It's half a volt per division. So our 1 volt, and for this probe, that equals 1 amp. Our 1 amp line is right there. We're getting almost double the amplitude. So when you're injecting into a low impedance, then that's what you could get. You could get double the current. So per the mill standard, it recommends that you reduce the level. Let's go back to continuous triggering. Reduce the level until you get the desired current. And there we go. Let's get a single trigger. That's pretty good looking waveform. I mean, that's a good representative waveform that looks similar to what we recalibrated. And you're getting a 1 amp peak. Actually, your negative going peak is a little more, like 1.5, almost. Quite 1.5, 1.3 amps. But I go with that.
Q value is off.
What's that?
Your Q value is off. It's a little, what it'd be low or not?
It's well, that's your closest to 50% right there. That's your 4. Well, four is a little higher than 50%. 5 is a little below. And we said 4 or 5 was the range you wanted to be in. So
4.
yeah, 4 or 5 is ideal. But 3 was just barely outside the range. So if you're in the 3 to 4 range, that's pretty good. But here we're kind of in the 4 to 5 range, so that's ideal. So, and then if you were doing the full 10 amp injection, then you would want to put some attenuation on the output of the current code. So that, primary attenuation, and the attenuation that's still in is to get the drive signal so that you can drive the amplifier to near, to its higher end of its range where it's most stable. But then the other place where you might need attenuation is at the output of your current probe. If you're trying to measure, if the signal that you're trying to measure is more than the range of your scope. So anybody want to see that? That's about the last thing that I would want to show you. Well, what the hell?
Yeah.
I'll show you. It's only 10:30. So, what's that?
Feeder the onion.
Yeah. All right. So we take the 20 dB attenuation out of our drive signal. So here again, it's not cookie cutter. It's not always put 20 dB in line with your. It's, that's a tool in your kit, depending on the drive signal you're trying to get and the capability of your equipment. If you have one of those other systems that I was talking about, like I said, I can't remember the name of the manufacturer, but if you have some other system that they may have broader dynamic range. You might be able to get some of those lower signal levels, more, in a more stable way. So it's just that's a part of the whole point of the pre-calibration step is to look at the signal that you're getting and make any adjustments that you can. Now your options are kind of limited, but you can put some attenuation in, get a beefier drive signal, and what have you. But it's all about thought process more than providing an answer. That's not always very satisfying, but that's engineering, isn't it? So, oh yeah, I'm just gonna do 20 dB. Yeah, these are both 20 dB and 25 watts. So these are 25 watts. That should be fine. I think these are bidirectional. Yep, they are. It says so right there. So,
Yeah.
Um, it's generally a good idea to keep the current probe isolated from the ground plane. If your point is sufficiently non-conductive, it shouldn't matter, but I'm going to put our isolator back in here. Just with that in place, it was a little awkward. I'm going to go ahead and put this here. Keep that stable. Okay. So now we've got the signals coming just directly out of the signal generator going to the probe, to the injection probe. So there's no 20 dB attenuation in there anymore. But now the current probe has 20 dB of attenuation in line with it. Because we're expecting 10 amps, which is going to give us 10 volts at the output connector. 20 dB is going to knock that down to 1 volt. Now we're going to need to adjust the amplitude here, but that's the range that we're looking for here. So turn it on, enable the output. What do we got over here? Okay. This is updating, right? Yeah, okay. Actually, that's pretty darn close.
Yeah.
Which makes sense, right? We removed the 20 dB attenuation from the drive level. The drive level is still the same coming out of the generator. So, so the signal on the scope looks the same, but it does mean something different now, right? That's what you have to pay attention to. So I'm going to go ahead and adjust the level so that we're getting closer to our 1 volt. We can adjust our horizontal resolution to get a little better look at that first peak. And again, when you select these waveforms to put in the test report, you can take as many scope captures as you want. Nothing says, oh, you got to capture everything in one capture. So I'd be inclined to get something like this so that you get a good look at the first peak. And then I guess you could take something like that if you want, but then that gives you like that would be an essential one for the test report. And then maybe just the one expanding around the first peak. But and then highlighting that yes, we're getting the decay that we want. But yeah, this waveform looks pretty much identical to the one that we just looked at, but now it's representing something different. Right? That 1 volt leading peak, that's still 50, wait, I'm sorry. That one, getting ahead of myself or behind or whatever. The 1 volt on the scope, working backwards, we'll pick up the camera here. Like this is the sort of stuff that you need to do like all throughout the test process. and bounce it off of everyone in the room, because it's real easy to get confused, right? Like I am right now. It's really easy to, maybe do that factor 10 multiplication in the wrong direction or whatever. Have everyone in the test environment check the numbers to make sure that what you're getting is really what you think it is. But so that 1 volt that you're seeing on the scope is on the output side of this 20 dB of attenuation. So it means that 1 volt is 10 volts here. And that 10 volts here at the output connector, the current probe, means 10 amps through that wire. That's a pretty beefy amount of current to put through that wire. But again, it is a transient. I'd be a lot more concerned about that if it was, 10 amps constant. But that's 10 amps of current through the wire. And then, the drive signal through our probe here to give you that current, or give you the potential that is producing that current. So anyway, that is what I had to show you. Does anybody have any questions? Or would you like to see anything else or see anything again?
Yeah, John, you know about those frequency boxes?
Oh, yeah, thank you. So for CS116, we generally, I'm gonna turn this off. I'm actually gonna shut it completely off. But we generally just use this box for CS116, and it's generally sufficient for our needs, right? The discrete outputs. Like I said, for RST, where our concern was kind of in between 1 megahertz and 10 megahertz, so we just said, all right, well, we'll just apply those 2 levels at those 2 frequencies. But the EMI guys last week found these boxes here. Where did you find these things?
Up in the cage.
They're just up in one of our storage cages. These are, no, this one's turned around, but there's a module that they basically go with this box. They're like auxiliary units that connect to this 9354. So they're the part number is 9554 dash whatever frequency range here. So this one's 10K to 1 meg, 1 meg to 6 meg, 6 meg to 50 meg. So different frequency ranges. This top one, I'm pretty sure, is 10K to 100K. So it's these external modules that give you variable frequency module. You can get any frequency in between those extremes. So if you really need it, if 1 megahertz and 10 megahertz were not sufficient, and if you really had a strong need I need to get 3.5 megahertz, then you could go to the appropriate module that covers that range. That'll be this one, 1 megahertz to 6 megahertz, and dial in that frequency. Now, they just found these boxes and put them down here like Friday, so I haven't had a chance to play with them. And they plug into, they're not standalone, they plug into the back of this unit. And so we haven't tried that, and I'm not about to try something like that for the first time in real time with a live audience. But that, talk about test and measurement fundamentals. That's a presentation fundamental. Don't do that. Don't do something for the first time in front of a live audience.
We'll do it live.
What's that?
We'll do it live.
We'll do it. I have tried that, and sometimes you get lucky, but you don't want to rely on luck. So, but if you do find a need to be very specific with a frequency that you want to apply, then these boxes do exist. And they're also made by Solar. They're basically accessories to these things. I can't really envision a situation where something like that would be necessary, but if you wanted to really get specific about characterizing the response of your equipment to a range of frequencies, then at least this type of equipment is available. So, in fact, you can see the back of this top one. This, I think that's just a banana lead that plugs into the back of this unit.
Right.
And then you also need like an RS-232 or something.
Yeah.
So we haven't done that. Oh, that's pretty cool. I'm giving you the infinite regression thing here. Somebody posted that picture of Alfred E. Newman reading a copy of Mad Magazine with him on the cover last week. So that you're getting that effect right here. Oh, and even the delay. All right. I started the session off with talking about Pink Floyd, so I guess that's kind of appropriate, right? There's your damn sinusoid. All right, anyway. I think that might be a pretty good indication that it's time to wrap it up. Does anybody have any other questions or concerns or thoughts?
There was someone in the Teams call with their hand up.
So there's somebody with their hand up?
He's had his hand up since the beginning when you asked, but.
Oh,
Oh, right.
I wasn't sure how, I knew it was up for a while. I didn't think it was that long.
Oh, I guess I'm maybe supposed to,
He requested a sign.
yeah, it was asking for the I'm okay signal and he provided it, so here we go. All right, well, all right, it's 11 o'clock, so thank you all for participating today. Hope you got something out of this. CS115 and 116 are tests we don't really run as much of as a matter of course as some of the other tests, but like anything else, it's just good to know how to do them when the time comes. And they do have their place. Like I said, the Roman example where we had those transients from the propulsion drive. Like, yeah, this is maybe a good thing to verify that this isn't going to be a problem on the platform. So it was good that we did that and retired that risk. So with that, thank you all and have a good week.